Hi, my name is George Bornstead, and originally this award presentation or introduction was supposed to be made by Willie Solano Flores, but he had a conflict, and so Felice asked if I'd step in, given that I'm going to be chairing that committee next year. But I think most of you know that the E.F. Lindquist Award honors distinguished scholars and researchers in recognition of outstanding research in the field of testing and measurement. And it's an award which is co-sponsored by both AERA as well as ACT. And the 2018 awardee was Charles Lewis of Fordham University. And I want to read from you the citation that he was given as a way to introduce him to you. Dr. Charles Lewis is a professor emeritus at Fordham University and distinguished presidential appointee at the Educational Testing Service. During his highly productive career, Dr. Lewis has made outstanding and widely cited contributions in key domains of psychometric research and educational statistics, including hypothesis testing, multiple comparisons, Bayesian statistics, factor analysis, differential item functioning, test construction, and computerized adaptive testing. He's been a wonderful mentor and a highly effective teacher with an uncanny ability to grasp complicated topics quickly. Dr. Lewis has deeply influenced generations of scholars and practitioners through his research contributions and his one-on-one interactions. He received his PhD in statistics from Princeton University and has taught at Dartmouth College, the University of Illinois, and the University of Groningen. So it's my pleasure to introduce Dr. Charlie Lewis.
Thank you. Is that going to be good? Yeah, we'll see. Okay. Thank you very much. I really appreciate that. And I really appreciate the opportunity to speak to you guys today and about something that I enjoy talking about, and hope you'll enjoy it as well. And I guess as far as questions are concerned, we'll have questions at the end. Is that the? Okay, so it would actually be more fun if you could ask the questions as I go, but I guess that's.
But I'm not going to give you 3 minutes, 2 minutes, 1 minute.
No, I got that. I appreciate that. Okay. All right, so the topic today is a Bayesian look at reliability. And what I really want to convey is, if this works, is a sense of fun. If you can believe that there could be something fun about reliability and Bayesian ideas, but that it's actually kind of fun to play around with these ideas and to sort of think about different implications, different ways of understanding situations. And there's almost nothing in this presentation today about estimation. So one thing you might say, well, there's nothing actually practical in here. This is all sort of theoretical, and just sort of think about it. And I think that's maybe, as somebody who's 76 years old, that's time for me to back off of the the estimation and the heavy-duty computation and sit back and try to think about things while I still can. So that's where we are. All right, so let's see. What have we got here? We got a mouse that does not do what oh, there it goes, son of a gun. Okay, so I'd like to formally begin with making 2 acknowledgments. The first one is to Mel Novick. That's a picture of him. And he was a man who first introduced me to classical test theory in general, reliability in particular, and even gave me a feeling as a graduate student that doing research about reliability might actually be interesting and fun and worthwhile. So, and then a few years later, after I had graduated and was at University of Illinois, he was at University of Iowa, and I have to mention, because of this lecture, He was in the newly built Lindquist Center at the University of Iowa, and he and I worked together several summers, and at that time he stimulated my interest in the idea of doing research in Bayesian statistics, and in particular in what are called multi-level or hierarchical models, and the ones we're going to be talking about today are about the simplest examples of that sort of thing. So I want to very much acknowledge A, his contribution, and B, in particular for my individual interest. Okay, acknowledgement 2 is a more up-to-date acknowledgement, because I have to confess that I kind of left the world of reliability in my research for a number of years, and spent time on other things. But a few years ago, Andre Ripp, a colleague from ETS, who is the lead developer for the NCME's items portal, got in touch with me and a former student, Michael Kajewski, who's at Kaplan now, and asked us if we would be interested in working with him to develop a teaching module on reliability in classical test theory. And so, why not? What else you got to do in your retirement, right? So we had a lot of fun working on that, and Andre was really a wonderful person to work with, and he made sure that we got things done. And so if you want to take a look at this thing, there's a address there, but you could just go to the NCME website and look for items, and you'll find it. There are a bunch besides ours. We were just one of several. Okay. This is a slide that Andre gave me that sort of is like an ad for items. You can see there are a couple of screenshots. It's pretty classy. He had a lot of fun working on that. Okay, so now to get to the more dry list here. This is an outline of what I hope to talk about today. So first I want to talk about, in sort of general terms, the role of statistical models. And then I want to move on to that to talk about classical test theory and reliability, briefly review some of the ideas there, and then bring in empirical Bayesian interpretations of those ideas and show that those lead to slightly different ways of expressing reliability, and then make a comparison between Bayesian and standard interpretations, and then finally, just for fun, take the Bayesian approach and apply it, get out of the classical test theory world and apply it into item response theory, show that there's a natural flow and generalization in that setting. Okay, so that's where I'm going with this. So we start with, I have a list of about half a dozen quotes of this, that, and the other thing, and this is one of my favorites. This comes from a man named George Roche, who is identified with a certain item response theory model, and he's a Danish mathematician who wrote this in 1960, so you think of that, that's almost 60 years ago. This is ancient history. And what did he say? And this is, remember, Danish was his first language, so don't pick on his grammar. Let's just focus on the result, what he says. That the model is not true. He's talking about a particular model he described in his book. He described several different IRT models. That the model is not true is certainly correct. No models are. Could just stop right there. No models that we use in practice are true. So, what's his point? Models should not be true, but it is important that they are applicable. What does he mean by applicable? Well, as far as I'm concerned, you can apply them in a variety of ways. The way I want to talk about applying them today is that they may aid us in understanding phenomena in the real world, in spite of the fact that they're wrong. So the fact that they're wrong shouldn't get in the way of helping us understand what's going on. We have to be careful working with things that are wrong, but that doesn't mean we shouldn't work with them. Okay, so now we go to my brief discussion of classical test theory. And as I was practicing this today, I thought, after just saying all models are wrong, now I write down on this page a model that as it stands here is not wrong. So Okay, it's not right either. It's a meaningless model at this point. It needs some more specification in order to become a model that is wrong for sure. For instance, you need to have if you could have a couple of parallel tests, well, then you know, of course, it's impossible to have exactly parallel tests, so therefore a model that assumes parallel tests has got to be wrong. All right, but let's just go through the very simple expressions here. So the basic idea of classical test theory is to think about taking a test score, an observable or observed test score, and breaking it up into two components, thinking of it as the sum of a true and an error component. And the true is the thing that we, at least with this test, intended to measure, or are measuring whether we intended it or not, the systematic part, and then there's some kind of noise coming in there that's represented with the error. And we assume that the true and the error components are uncorrelated, and the net result of that is that we can take the variance of the observed scores and write it as the sum also of two components, a true variance and an error variance. And the interest, this is where the idea of reliability comes from, is talking about relative to that variance in the observed score, how much of that is due to the true score and how much of that to the error. So that's what reliability tries to capture and tries to summarize in a single number. Okay? So nothing very earth-shattering about that, but this is, that's where we are. Okay, so now let's look at a definition. There are actually lots of definitions in the literature about reliability. For instance, definitions that involve parallel tests, just as an example. But this is the one that, for whatever reason, Fred Lord and Mel Novick, back in 1968, when they were writing their test theory book, decided to take as the actual definition. They said, let's define the reliability. Here I just abbreviate that with REL. As the square of the correlation between observed scores and true scores. Okay, so that's the idea. We know correlations are ways of representing relationship, and a squared correlation sort of has a nice flavor, so why not? It's a little weird, though, if you think about it, in the sense that how would you ever take a correlation like that? Well, you've got the X, which is observable, but then you've got this T, and that's not observable. In fact, there's a term that people sometimes use for theoretical quantities when talking about theories in science, and that's a hypothetical construct. And I love that term, and I think we could talk about the true score as being a hypothetical construct. It doesn't have any real existence. It's hypothetical. It's something we're thinking about. It's a construct. We constructed it as part of our model. So here we're talking about the correlation between two variables, one of which is observable and one of which is a hypothetical construct. So now you get the idea. This is thinking about stuff. It's not, oh, let's go out and calculate it. Let's collect a bunch of true scores and observed scores and find out how correlated they are. No, we have to think about it. And we can think about correlating these two variables. And in fact, the idea here would be that we imagine that there's some population, because in order to take a correlation, we have to have a population of individuals, test takers, potential test takers, each of whom has a true score, hypothetically, and each of whom could have a observed score at X if we actually gave them the test, and we could imagine taking the correlation in that population of those two things. So use your imagination is the idea. Now then, we can, because of the basic variance component structure, the variance of X equals variance of T plus variance of E, we can rewrite that reliability formula definition as a ratio of two variances, the variance of the true scores divided by the variance of the observed scores. And in this form, I think it's easier to think about, easier to interpret. So this is like, there's one thing is definition, and the other is how do you think about something. Here we can say this is, in this form, reliability is representing the proportion of true score variance, of observed score variance that's associated with the true variance. All right? And if you prefer to be so this is the glass half full formula, and then we have a corresponding glass half empty formula. If you want to, you think about, oh, but there's all that error. Okay, so you can look at the ratio of the variance of the error scores to the variance of the observed scores. And so that's, how much out of that total variability in X is noise, is the stuff we're not actually picking up on with our tests. It's just lack of systematic variability. And then that ratio, subtract that ratio from 1, and that gets us back to our original reliability. Okay? And we could keep going. There are a bunch of other formulas we could generate. I'm going to look at 2 more, but instead of looking at them the way they were first introduced by a man named Truman Kelly back in the 1920s, when classical test theory was still really classical, we're going to look at them with a Bayesian pair of spectacles. Okay? So let's see. All right, so here we go. Bayesian approach to classical test theory. Now we start having models that can really be wrong in serious ways, okay? So let's watch out. That's generally a phenomenon, by the way, with a Bayesian approach to anything, is you have to have a more formal model, typically, in a Bayesian approach than in other approaches. And that means there's more things that can and will go wrong, so be careful. All right, so the first, so we have 2 different expressions here. We're not throwing away the x equals t plus e, by the way. We're just now specifying a little bit more about what's going on. And that same breakdown of variance of x equals variance of t plus variance of e still holds here, but let's just keep going. So the first thing is we're going to say that this distribution of true scores in a population of interest actually has the form of a normal distribution. Okay, so that's a pretty strong, we call that a very parametric model. And so we're imagining that it has a normal distribution, and it has some mean, and it has some variance, and that variance, that's our true score variance, there it is. And from a Bayesian perspective, we refer to that thing as a prior distribution. Prior what? Prior because it's something that in theory you might have before you collected the data, before there were observed test scores, there were true scores. But again, that's hypothetical, but okay. Then the second level here is the likelihood form. And here, the way we do that in from a Bayesian framework is we don't talk about the distribution of E or the distribution of X, but we talk about the conditional distribution of the observed score given the true score. So the distribution of the data we're going to collect if we knew this unknown parameter. And there we're going to, again, assume that that distribution is normal, but now the mean of the normal distribution with X, conditional on T, has a mean of T. So T is the mean of that conditional distribution. Or another way of saying it is the mean of that conditional distribution is the hypothetical construct, the unknown that we're interested in. Okay. So I think I've got a slide here. No, that's going to come up in a second. Okay, so so first stage is the prior, second stage is the likelihood, and those are the 2 pieces that you need to use Bayes' theorem. So we're ready to go, except, we got to stop for a second. This is different from the kind of simple Bayesian model that you'd get in a first-year course on Bayesian statistics, in that there isn't just a single unknown parameter, there's actually a real population of unknown parameters, one for each person in your potential test-taking population. So that means that this prior distribution for the true score is actually a real, quote-unquote, real distribution. If you can have a real distribution of a hypothetical construct, I don't know. But anyway, it refers to, it's a kind of probability distribution that you could imagine arising through sampling. So you say, I'm going to randomly sample a person from this population, and they've got a true score, and that creates a distribution of true scores. And the contrast is with a typical Bayesian approach. You might say, well, my prior distribution reflects my uncertainty or my beliefs, the strength of my beliefs. It's more of a subjective probability. And that's one of the standard objections that people have to using Bayesian methods. They say, don't bring all that subjective stuff into my statistics. And no, so this is, those people should be really happy because this prior distribution is absolutely on the same footing as the distribution of X given T, okay? And in fact, this idea of the set of population parameters that I mentioned, I'm not going to go into it, but this is a very simple 2-level model, hierarchical model, okay? Where you have a true score level and then given true score and observed score level. So it's a 2-level modeling setup, okay? All right, so yeah, here's the picture, good. Okay, so the top normal distribution represents this prior distribution of T, And now I'm imagining that we just sample two different values, T1 and T2 there. The T1 is the smaller one, T2 is the bigger one. And then below are the distributions for the observed score given each of those. So given T1, we get that normal distribution for X for the observed score. And you see it's centered. It's supposed to be at least centered on T1. And the other one for T2 has the same. We're assuming homogeneity of residual variance or error variance. But here it's the mean is set at T2. Okay? So you can, looking at that picture, you can just think, yeah, that model is so wrong. And that's good. Then you're with me. That's right. This is a model that's really wrong, but hopefully will still be helpful for thinking about what's going on. All right. So now we use Bayes' theorem. We combine prior and likelihood. And when we do that, luckily somebody has done that before us. I don't think it was actually Bayes, but it might have been somebody in the 19th century. And they said, well, if you have a normal prior distribution and a normal likelihood, and you combine those, presto, the posterior distribution is also normal, and it has a particular form for the mean and a particular form for the variance. So you don't actually have to use Bayes' theorem here. You just have to say, oh yeah, I know this problem. That's in a textbook that I saw one time, or it's on Wikipedia or whatever. Okay, so there's a formula there. I'm not even going to read it for you, because we're going to go and we're going to look in more detail, because what I want to do is I want to look at the mean and the variance. I guess I could say one or two words about what a posterior distribution is from a sampling point of view. Okay, from a sampling point of view, we're talking about the distribution of t given x. So what you have to think from a sampling point of view is take all the test takers in this population with quote unquote the same test score, and look at each one of them has a true score, look at their distribution. That's the posterior distribution for t given x. Okay, it's not a subjective probability or certainty or anything. It really refers, in this setup, to a population, a subpopulation defined by the observed score. Okay? So, now we've got that form, and now we want to make use of something we introduced at the beginning, namely the definition of reliability as the ratio of the true to the true plus error or observed variance. And then we can rewrite the posterior distribution using that notation, but let's now flip right to that. So here is the mean of a posterior distribution for t given x, and it says that the posterior mean for t given x is equal to the value of the reliability multiplied by that observed score plus 1 minus the reliability multiplied by the mean of the true scores, where you say, where did that come from? Well, the mean of the true scores is going to be, by classical test theory, the same as the mean of the observed scores, so that's not a real stretch. That's okay. All right, so this formula was actually this one that Truman Kelly introduced back in the 1920s, and it's safe to say, to estimate true scores, for sure, and it's safe to say that Truman Kelly did not use Bayes' theorem to do this. Almost certainly what he did was to use, he didn't go into a lot of detail when you read about it, he just writes the formula out and says, there it is, guys. What he did was he used linear regression. He said, we've got an x, we've got a t, x is the predictor, t is the outcome, I want to fit a straight line, what would the slope be? Oh my goodness, the slope comes out to be the reliability. And the intercept comes out to be the mean of the scores times 1 minus the reliability. Cool. All right, so that's Kelly's formula. But, as was first pointed out to me by Mel Novick, this is for sure, this is Bayes' theorem. This is a posterior mean. And so whether Kelly knew that or not, that's fine. And it's telling us a way to use information that we have, namely the observed score, to say something about something we don't have, this hypothetical construct, true score. Okay. Similar story, we go to the posterior variance. It can be rewritten as the prior variance for true scores multiplied by 1 minus the reliability. And again, that formula should look very familiar in terms of a regression formula. This is like the residual variance in a regression. And if you take the square root of that, that has a name in classical test theory, namely, it's called the standard error of estimation, or the square of it is the squared standard error of estimation. Just like the variance of the e's is called the standard error of measurement for some reason or other. Okay, so you have standard error of measurement is the variance of E, and standard error of estimation is this thing, the posterior, from our point of view, the posterior variance of T given X. All right? So, start with that formula, do a little algebra, solve for reliability, and guess what? There we have a new formula for reliability. Reliability equals 1 minus the variance of the true score given X, namely the posterior variance, divided by the prior variance. Okay? So this is a whole new way of thinking about reliability. And again, this is the glass half empty story, but it's saying you start with a prior variance, which is this variance of T. You introduce the observed score X, and then you have a variance of T given X, which is sort of the part of T that you couldn't predict using X. And we would like that ratio to be small, and 1 minus that ratio to be large, and guess what? Algebraically, it's identical to the classical test theory of reliability. So it's another way of thinking about the same classical test theory concept, okay? Now we can get one more expression, and in order to get that, we need actually what is one of my, can you have a favorite equation in statistics? Sure, why not? Probably everybody has it. We should vote, what's your favorite? This is, I don't know if it's you might think, because I've done a lot of stuff with Bayesian statistics, that Bayes' theorem would be my favorite equation in statistics, but it isn't. I don't actually like it that much. But I like the result, but this is the one I really love. I don't know why, but I just do. Maybe it was, what was that? It was a sensitive period, or, it was ready to be imprinted. So what does it say? Now, not just for truths and observed. This is a very, very general formula. I call it an analysis of variance formula. It's talking about conditional variances and means. And what it says is a variance of any variable, when you got another one you can condition on, can be written as the variance of the conditional mean for that variable plus the mean of the conditional variance. So it almost kind of rhymes, Variance of the conditional mean plus the mean of the conditional variance. Okay, so, all right, so that's a formula here. I apply it to true scores and observed scores and make sure that the average of T given X, well, that's the posterior mean, and the variance of T given X, that's the posterior variance for true given observed. And together, the variance of the conditional means plus the mean of the conditional variances gives us the variance of the prior variance, the variance of the true. Okay, now this thing gets simplified because, well, okay, so then in particular we can write the, going back to our glass half empty formula and then solving, we can write this as the glass half full formula, which says that the reliability can be thought of as the variance of the estimated true scores divided by the prior variance of the true scores themselves. So if the estimated true scores have almost as much variability as the actual true scores, that's a good thing. And if they have a relatively small variance, that's not such a good thing. And the reliability, again, reflects that as a fraction. Now, I have to tell you one little story. Am I too terrible on the time? Yeah, a little bit, but okay. One little story about this, and I don't want to embarrass Emily, but I'm going to. No, it's not an embarrassment, because she was... You'd think, okay, the way I'm telling this, that, yeah, I've known this all the time, and I always use this, and I always think about this. But there was a time when Emily and I, former student Emily Bowe, were working on a paper together, and I forget exactly what the context was, but this was something with IRT for sure, and which we're going to get to, I promise, and she was using a formula that looked like this, basically, except for IRT. And I said, Emily, you must be using the wrong reliability formula because you've got the variance of the true scores in the denominator, and everybody knows the variance of the true scores has to be in the numerator. It's the variance of the observed scores has to be in the denominator. And Emily said, would you look at page such and such in Lord and Novick and read about Kelly's formula? And I said, well, actually, I have read that before, but it's really nice to have students who can remind you of that. So here it is. Thank you, Emily, for reminding me. All right, so here's just a summary comparison. What I've called the standard approaches, where we're looking at things as a proportion of the variance of x, and the Bayesian approach, where we're looking at things as a proportion of variance of the true scores, the prior variance. And again, one way you can think of it is, in the standard approach, it's telling you, if you knew what the true scores were, how well would you be able to talk about the observed scores? And for the Bayesian approach, it says, if you knew what the observed scores were, how well would you be able to talk about the true scores? And so the way Bayesians always like to tease non-Bayesians about this is they say, yeah, you guys want to say, given what you don't know, let's make probability statements about things we do know. Well, guess what? In Bayesian statistics, what we do is we want to start with the things we know, and we want to make probability statements about the things we don't know. It seems more like what science should be, right? Okay. Well, actually, the way it works in standard statistics is we do this complicated inverse reasoning. You say, well, if this were true, then that, but it doesn't look like it is true, so therefore the other one must be true or something like that. You know, reject the null hypothesis stuff. Okay, so there's another way. Okay, so now, quickly, IRT. I'm not going to do a lot with that because I can see I'm chugging right along here. Same layout, prior, likelihood. We can take the prior to be normal again. In fact, in IRT, we could have, specify the mean and the variance for most models, except for the Roche model, because the scale is not set ahead of time. So we'll set the variance. So we know, in this case, we know the true score variance is 1, which is kind of cute. And then we have a likelihood, which is the standard thing we work with in IRT, where it's a product of the probabilities, the conditional probabilities of the item responses given the latent trait, using conditional independence. And then we're going to combine those two, and it's going to get immediately going to get very yucky. And there it is. And that is Bayes' theorem. There is Bayes' theorem applied to IRT. And guess what? It didn't come out to be a nice, simple, normal distribution with pre-specified formulas. Too bad. That's what we have computers for, right? So we can approximate that. We can do numerical integration and products and so on, and that'll be fine. And in particular, we're not so much interested in that whole distribution. We are actually interested in the mean and the variance, just like we were back with that normal thing in classical test theory. And the mean, okay, complicated formula, but again, can be numerically approximated pretty easily. That is, in the wonderful world of IRT, that is sometimes known as the EAP, or expected a posteriori estimator. That's nothing more than the posterior mean of the latent trait given the item responses. Okay? And similarly, we can talk about the posterior variance, which has a yucky formula, but again, can be numerically approximated. And this is a thing, the square root of that is sometimes in output for IRT programs is referred to as a standard error for the EAP. I don't really like that much, but okay, it's the posterior standard deviation, that's close enough. Okay, so those are two things that computer programs that fit IRT models often will generate for you. So there's Bayesian statistics at work, okay? And to go to reliability, we now go back to my favorite formula, and we make a decomposition of the variance of theta of the latent trait, and we can say that's equal to the variance of these EAPs, the posterior mean, plus the average of the posterior variances. Okay, same formula applies. It doesn't care whether it's classical test theory or IRT. Okay, so then we can define, because nobody did it before. Well, actually, it's been done before. I'm not making any new claims. So you'll find this again in output from many IRT programs. We can generalize the idea of reliability very easily by talking about the variance of the posterior means divided by the variance of the prior variance for the latent trait. And if, again, the glass half empty thing, we can compare the average of the posterior variances for theta with the prior variance for theta and then subtract that from 1. Okay? So, an idea that was floating around in classical test theory forever can be used just fine by people in IRT if they want to. I mean, some people in IRT don't think you should touch reliability with a 10-foot pole, but I think they're gradually being worn around. So, okay, so then, in fact, these formulas even get simpler in the special case, which is a pretty common case when the variance of theta is set to be 1. So then the reliability simply becomes the variance of the EAPs. Just look at how much, and then or 1 minus the average of the posterior variances. All right, so that was the El Quico generalization of reliability to IRT. And to summarize, yes, many different ways to think about reliability. We haven't begun to cover them all, but this, using a Bayesian interpretation, reliability may be understood as a measure of how much an observed score tells us about a corresponding true score. It doesn't mean that if you take a Bayesian point of view, you can't look at the standard interpretation. Those are also very useful for other purposes, so it's not an either or. You don't have to choose. I think having more ways of thinking about a quantity is actually a good thing, not a bad thing. And I don't see them in direct competition. They're just two different ways of slicing up the pie. And the, in mentioning here, the Bayesian interpretation also allows a natural generalization to more complicated models like those in IRT. So I hope that this gives you at least a little feeling of, if nothing else, how much fun I have with this stuff, and I hope that maybe you could have fun with it as well, thinking about things further and take advantage of, in particular, a Bayesian perspective, not only for reliability, but actually you could use Bayesian perspectives for a lot of things, so think about it. Okay.
Thank you very much. Questions, comments?
Yeah, absolutely. You've got a microphone, huh? All right.
No questions? Hey, Charlie.
Hi, Glenn.
So one of my favorite formulas in this context is the Spearman-Brown prophecy formula.
Yay.
And just thinking about your thoughts on the Bayesian approach to reliability in that framework.
Sure. Well, if you look at we're talking about classical test theory now, and the Spearman-Brown, for those few who have not been introduced to that wonderful thing, is imagining that you split the test in two parallel parts and then correlate them, and that gives you supposedly the parallel forms reliability of the half test, and then you use the Spearman-Brown formula and it boosts it up to an estimate or a prediction for the reliability for the whole test, which is, okay. The way I would see that formula is that it supplements what I've been talking about here in the sense that when I write down a formula, let's just stick for now with it does not matter. There's nothing in my formulas that, yes, let's just talk about the Kelly estimate as concrete. My formula says, okay, Kelly's formula says that there's a reliability there. It does not tell you how to estimate reliability. Kelly imagines that somehow or other, maybe with the Spearman-Brown formula, you've already estimated reliability, and then you can plug it in. So in that sense, in fact, I would say of a whole bunch of the formulas for reliability are actually formulas that help us estimate and compute. None of the ones that I put down, except for the IRT ones, interestingly enough. With the IRT one, all of a sudden, oh my goodness, we could actually, this is not only a theoretical thing, but we actually get these posterior means and posterior variances. We could plug those in and that's what people do. But all the other stuff, there was nothing in there about how to estimate reliability. So, the simplest version of estimating reliability is two parallel forms. Good luck. Then the second one, a little more practical, Spearman-Brown, split half. Then you want to get really fancy, Cronbach's coefficient alpha, So those are all formulas that are talking about reliability, but they're focused on the idea of, well, how would I actually get a number? How would I do this? And you can have, you can get really fancy and start thinking about factor analysis or structural equation modeling and have more complex ways of talking about things. And then Another direction to go is the way that people have gone with generalizability theory, where you're using ideas out of random effects analysis of variance and estimating variance components there. So all of that is out there and interesting and is, would supplement the sort of stuff I've talked about here. This is sort of like, however you estimated reliability, how do you think about it now? Okay, you've got this number, you've done your Spearman-Brown, now what do you do? Okay? Anybody else? Yeah, great.
I'm thinking about how we teach IRT
Yeah.
to people who don't have exposure to these concepts. And I'm wondering about what you recommend in terms of introducing the Bayesian concepts as a precursor to help them understand, or after the fact to reiterate. I'm struggling myself in the way I learned and the sequence, and what's helpful versus making it more complicated than it needs to be.
Well, if you buy the whole the whole story here, for me, the idea of being able to start with the classical test theory has a couple of advantages. First, it doesn't get any easier than that. This is a model that people can really get their heads around. I think a lot of times when we're teaching IRT, we start off by telling people how terrible classical test theory is, and I think that's too bad. And I think instead it would be nice to say, hey, let's talk about classical test theory first and then show the relationships and how we can build on what we've learned in classical test theory to deal with more complicated models that handle things that that classical test theory is not so good at handling. But so in that sense, I like the idea of doing doing the Bayesian thing, but not just plunging right in with Bayes' theorem for IRT, because it's a mess. You look at those things and you say, where did that come from? Whereas in the classical test theory with the normal model, you can really you can play with the formulas, but you could also draw the pictures, and you could I think people are more used to thinking about. Hopefully, they're more used to thinking about regression and a bivariate normal distribution and fitting a regression line, and and seeing the close relationships between the Bayesian inference and regression. I mean, you could say essentially in the classical test theory model that I presented, doing Bayes' theorem is just doing that's how Truman Kelly was able to get his answers, is just doing regression. So if the people have had regression before, at least they've been exposed to it, that gives them a simple in. And then you say, okay, now we're going to this more complicated thing, but the same ideas are there. They're not going to go away. It just means we have to do more intensive computations and stuff, but conceptually we're doing some things that are very similar. That help? No?
Well, that's how you taught it to me 45 years ago, so you still got it.
Thank you, Neil.
And also, and Fred Lord pointed out in his 1980 book that everything about IRT that he had in his IRT book complemented classical test theory, which is what you just said. But a lot of people make them.
That's another one of my favorite quotes, by the way. Yes, is that Lord says, is his book on where he first uses the words item response theory, right? Before he was talking about latent trait theory or something like that. Right. And then he said, he talks briefly about. So Lord follows my example, right? No, I follow Lord's example. When he's talking about IRT, he starts by talking about classical test theory. His first chapter is a review of classical test theory. And at the end of the chapter, he says, nothing in the rest of this book will contradict anything that we've talked about so far, but it will be able to answer some questions that classical test theory is not able to answer.
Yeah, so I love listening to this, just like I liked listening to it back 45 years ago.
Yeah.
And I guess the key thing here is that you can think about the true score as an EAP for the observed score to a certain extent, right? Is that?
Yeah.
And that's why.
Well, Kelly's formula is the EAP.
Yeah,
Kelly's formula is the EAP for classical test theory, yes.
For a true score, given an observed score. But
the
classical test theory, the definition of the expected value of the true score is defined as the expected value of the observed score given the true score.
Yeah.
So they're both kind of.
Yeah. Oh, yeah. No, I think there's a lot of parallels. Yeah.
And so when you're talking about non-EAP estimates of theta, this does not hold, right?
Well, That's an interesting question,
Yeah.
which I don't really know the answer to. This certainly works most naturally with the EAP, but what it's doing is it's taking a Bayesian point of view, and it's not, you might think it's like saying the EAP is like, maybe that's what you were saying a second ago, that the EAP is like your observed score. But no, that's really not true, okay? Don't say that. There is no observed score. There's a vector of observed item scores, and that's what you've got. So there is no observed score. Even if I wanted to write x equals t plus e, I didn't get the x to start with. So I can make up all kinds of different estimators. And for instance, if I use EAP, I can do that formally, and I can get a true score, but the true score will not be theta. It will not be the latent trait. It'll be some weird formula that depends on the item difficulties and stuff like that you don't want. Okay, so.
Well,
Hey.
thanks for the interesting talk.
Thank you.
When I see the parallels of CDT and IRT,
Yes.
Only difference is you use Y1 to Yn for IRT and
Right.
X for
Yes.
CDT, right?
Yes,
So
yes.
it seems to me that, if we use X1 to Xn, then all the formula applied to IRT can be used for CDT to
Yes. Oh, yes.
estimate reliability.
Yes.
And
Yes.
is that true?
I could not agree with you more. Yeah.
Okay.
Yeah. So, for instance, yes. Just let me. You want to say more? Go ahead. Say more.
No.
Okay.
Just I was thinking that in one context, the regression.
Yes.
The regression does a really bad job if the predictor has measurement error, and the one way is plug in, reliability estimate, or multiple indicator to use structure equation model. So
Yes,
the multiple
yes,
indicator looks like IRT, this Y1 to Yn. Kind of just a hunch.
Yep, I like that. Yes, there's several good points there. But let me just react to one of them, which is why did I use Y? Oh, just because it was different from X. But if we imagined each of those little guys like a observed score, each item score is an observed score, and for simplicity, now talk about models that are really wrong, let's even imagine that these item responses are continuous rather than, say, binary. And let's imagine that we can think about normal conditional distributions with them and all that kind of stuff like I was doing. Well, anyway, you can write down, for sure, one classical test theory model that you could write down that I have a soft spot in my heart for, because it was something that was used in one of the first papers that I was involved with Melnovic, is something called the essentially tau equivalent model. So we would say each of the item responses, the x1 through xn, can be written as the true score plus the general true score plus a constant that's specific to the item, so like an item difficulty, plus an error component. And then we can work with that model, and we can come up, for instance, one of the things we can do under that model is derive coefficient alpha as a formula for reliability. So it actually, coefficient alpha algebraically in a population is identical to reliability for the case of the classical test theory version of the Roche model, if you like. For sure, yes. So I'm not arguing with you at all there. Yeah, absolutely. All righty. Okay. It's been a pleasure. Thank you, guys.